Now, let us take an example in support of this. Suppose I take a function g f x equal to sine 1 by x for x different from 0. Okay. Then it does not have a limit at x 0 0. Then this function is not continuous at x equal to 0, because we cannot define the value of the function at the point 0, because at the point 0 the function f is not defined. Since f is not defined at x equal to 0, f is not defined at x equal to 0 because it does not have a limit, because this does not have a limit, is not defined as 0, because the limit of this sin 1 by x as x tends to 0 does not exist. And this we have seen already, that if we take x equal to 1 by pi, the limit of the function, limit of sin 1 by x, x tends to 0 will go to 0. When you take x equal to odd multiple of pi by 2, the limit of this function will go to 1, and like so on. Or there is a laws of fluctuation. In fact, if we go for the limit, then this is 1 by pi, 1 by 2 pi, 1 by 3 pi, and like this. So, there is a laws of fluctuations is there, like this, okay, something like goes. So, it has a positive negative value in the neighborhood of 0. So, the fluctuation exceed by epsilon, therefore, it cannot be continuous also, and again limit also we can say that does not exist. The second example, if we look the function f x, which is x sin 1 by x. Suppose I take for x is not equal to 0. Okay. The function in that case f x is not defined at x equal to 0, at x equal to 0. Then the function cannot be continuous at this point. Then f x cannot be continuous at x equal to 0. But however, if I redefine the function as follow. So, if we define if we redefine the function capital F x from R to R, means R to R, such that f of x, the value is 0 if x is 0 and equal to x sin 1 by x for x different from 0. If I redefine this function, then what happens? Then clearly f is continuous at x equal to 0. Why? Because the limit of this x sin 1 by x as x tends to 0 is 0, because it is dominated by x. So, limit will come out to be 0, which is the same as the f of 0. So, this case continuity follows. Therefore, this function, for this function 0 is the removable continuity. Okay. Okay. Now, there are certain properties of the continuous functions, which we will just some results or results on continuous functions, on combinations of continuous function, combinations of continuous functions. So, I will just state the results, and the result is for any arbitrary point it is 2. So, I will just give the general results. Let A, which is a subset of R, and let F and G be continuous on A, or at a point, let us take this f and g be continuous on A to R be a continuous function, functions A to R, be a functions on A to R, and let B belongs to R. Okay. Suppose that C is an element in A, and that F and G are continuous at C. Then the following results holds. Then F plus G, F minus G, F G, B F, and they are all continuous at C. And if H is a mapping from A to R, is continuous at C belongs to A, and if h of x is not equal to 0 for all x belongs to A, then the quotient f by h is continuous at C. So, the results follow. Now, this can be extended to a one as a corollary or theorem. The same results holds if f and g, let A which is subset of R, and let f and g be continuous on A to R, and let B belongs to R, then f plus g, f minus g, product f g and B f are continuous on A, and similarly B holds. Similarly B holds as above on the set A. So, I am not writing, that is what true. Okay. This one, the proof is just based on the earlier cases. We have seen the function f is limit function is there, limit of f x plus g x is limit of f x plus f x g x. So, based on this we can write down the proof for it. Okay. Now, another results are again without proof. Let A which is a subset of R, and let F is a mapping from A to R, and let mod f means absolute value of this f x be defined by mod of f x means equal to the modulus of f x for all x belongs to A. Then if f is continuous at a point C, belongs to A, then mod f is also continuous. At C. Okay. Then second part is if f is continuous if it continuous on A, then mod f is third continuous on A, is continuous on A. Similarly, if our domain, if A is continuous, if f is a, if f x is greater than equal to 0 for all x belongs to A, for all x, then the following result. So, then f is continuous at a point C belongs to A, at a point C belongs to A, then then under root of f is also continuous at C, and if f is continuous on A, then under root f is also continuous on A, where under root f x is defined as the under root of f x for x belongs to A, x belongs to A, and f of x is greater than 0. That is what. So, similar results holds, and we are not proving giving that, because it is very easy to show the proof of all these results. So, we are just skipping the proof for it. Okay. Now, next result, which is interesting, composition of the continuous function. Composition of continuous functions. Okay. Suppose we have the function f and g, both are say one is continuous at some point and other is also continuous in a point where the range set is contained in this, then we get the So, let us let f is a mapping from A to R, B is a continuous at a point C. Let this is continuous at a point C. If f which is continuous at a point C, and if G which is a mapping from B to R is continuous at a point B, which is the image of C under F, then the composition function G composition F is continuous at a C. Okay, function at a C. And here we assume that image of A under F is contained in B. So, the function is well defined, domain is this, and G f x means G of f x. This is the meaning. Okay. So, let us see the proof of this. This is the result. What he says is, suppose I take this one, suppose this is the set A, this one is the set say B, this one is the set say C. F is a mapping from A to B, G is a mapping from B to C, okay, and this. Now, what is given is f is continuous at a point C. So, here we are getting f of C, that is equal to B. G is continuous at a point B. So, here you are getting G of B. Okay. So, since G is continuous at the point B, G is continuous at a point B. So, what we get? So, there is a let us take a epsilon neighborhood of G B. So, let W be an epsilon neighborhood of G B. Let us consider this epsilon neighborhood of G B. Say here, this is in this inside, this is epsilon neighborhood of W. So, this is W. Take the epsilon neighborhood of W as an epsilon neighborhood of G B. Now, G is continuous. Since G is continuous at B, so there is a, since G is continuous at B, so there exists a delta neighborhood V of small b, which is the value of the function at C, such that whenever the y belongs to the B intersection of V, then G B image of this y under V belongs to W. This is by definition. So, what he is saying is, if I picked up a, for corresponding to this epsilon neighborhood, we can find a delta neighborhood of this, that is V, such that whenever the any point lies in the intersection of V and this, the image will fall within this range. So, by definition of the continuity of G at a point B. Now, further G is giving to F is giving to be continuous. Further, F is continuous at a point C. At a point C, this is given. So, there exists say gamma neighborhood of C, gamma neighborhood say U of C, such that if x belongs to A intersection U, then the image will go, f x will go to B intersection V intersection B. So, that, so what we get, the composition mapping G of f x, this will be equal to G of f x, and that belongs to W. So, what he says is that if since f is continuous at C, so for given this delta neighborhood of this, we can find a gamma neighborhood of C, such that the any point which lies inside this gamma neighborhood, gamma intersection A, the image will go to V, and every point which is in V, the image will go to W. So, G composition f x will go to W. That is what is said. But since W is, since W is an arbitrary epsilon neighborhood, W is an arbitrarily small epsilon neighborhood of G B. So, this shows that this implies that G composition F is continuous at C, because for any arbitrary small epsilon there exists a neighborhood say gamma neighborhood of say U of point C, such that image of any point 1 holds, such that 1 holds. So, this implies this is continuous function for this. Okay. So, we get this now we wanted to do some more maximum minimum also. For that let me just define the maximum and minimum theorem. First, the definition: maximum and minimum We have already stated the local maximum, local minimum. Here just it will be required definition. Let A be a subset of R and let F which is a mapping from A to R. Okay. We say F has an absolute maximum. F has an absolute maximum on the set A if there is a point, say x star in A such that the value of this x star under F will always be greater than the value of f x for all x belongs to A. Then we say the function f has an absolute maxima on the set A. Then we say f has an absolute minimum on A if there is a point, say x star, if there is a point x lower star I am saying belongs to A such that the f of lower image of this lower x star is less than equal to f x for all x belongs to A. Then we say x star is an absolutely then lower absolute minimum for it. The x star called the absolute maximum point, x lower star is called the absolute minimum point if they exist. X star is called the absolute maximum point and x lower star is called the absolute minimum point if they exist. Okay, and let's see. So we will continue next time this one. Thank you.